Okay, we're going to do our polar graphing today. I'm going to try and do it split screen because the graphs that I draw are not very pretty. So it'll be better if I can just type them in and then you can look at them on your graph on this graph on Desmos. But the first thing that I want to show you is how I got the graph to look like this. Before we had our grids just in XY fashion, but we're going to switch to polar graphing, which means that we're talking about the angles around. If you notice, these are our angles from our unit circle. So if you're in Desmos, if you hit the settings, which is this little wrench looking thing, instead of having it on grid, you can click it to grid, but we want to click the polar picture. So this is the polar graph for that. So once you do that, it'll be set up to where you can see it a little bit better. So you'll have to know how to do this for your test because you'll make another picture on Desmos with your polar graphing that you're going to learn. So you just go and instead of having the grid, you click on that one. Okay, so now that that's done, I'm going to go back and I'll let you know how we plot points. And then we're going to go through 5 or 6 different types of graphs. We're going to make some that look like flowers, some that look like hearts, some that look like infinity signs, some spirals, using our polar graphing. So this is polar graphing. Come on, pen. Thank you. So like I said before, we don't have an X and a Y for our coordinates. Instead, for our coordinates, the way that we graph them is with an R and a theta. So R stands for obviously our radius or our distance from the center, from our origin. That's our pole. That's how we talk about polar graphing. If you think about like magnets and stuff, I guess that's a sciencey thing. So we have our radius. And theta stands for the angle from the x-axis. Okay, and we can plot points. We'll be given what angle, where angle they are, and also how far away from the origin they are. So if I were to graph, say, 3 pi over 4, okay, I don't know that I can write on this. We'll see. I would go to pi over 4, which we know where pi over 4 is, and go out 1, 2, 3. And it would be right there. So apparently I don't have my ink on to write on this page, so I'll just draw that picture. I'll use my graphing more for that. So I've got 1 radius, 2, and then 3. And I want to go to pi over 4. So pi over 4 is here. So pi over 4, 1, 2, 3. And that's the point 3 pi over 4. Okay. I'll do just a couple more of the plots before we get into our regular graphing. Let's say that we had a negative angle, because sometimes that happens. If I was at 2, then negative pi over 2. So remember, pi over 2 is here, and negative means you go clockwise rather than counterclockwise. So I'm going to go negative pi over 2, and my radius is at 2. 1, 2. So that's where that point's going to be. So that point is 2 negative pi over 2. Sometimes you also have a negative radius, not just a negative angle. You can have that, which means that once you figure out what angle, where your angle is, you backtrack. So you don't go forward, like if I was at negative 3 pi over 4, I'll do that one, negative 3 pi over 4. So I go to pi over 4, okay, I'm at pi over 4, but I'm not going to go 3 positive direction. I'm going to backtrack and go 3 the other way. So you stay on the same line. So if you have it on the pictures, like this is 1, 2, 3 pi over 4, you're going to go backwards, but you just stay on that same line. But that's hard to do. It's hard. There's so many lines there, but you're just going to go backwards 1, 2, 3. So say this is my pi over 4, 1, 2, 3. This one is negative 3 pi over 4. So from the origin, you backtrack rather than going forward in the circle. Okay, so that's just plotting points with an R and a theta, radius, how far from the center, and your angle measure, just like you're thinking about the unit circle, you'll go to that point. And we use this polar graphing, and now we can make different shapes with sines and cosines and whatnot. Okay, So now we're going to go through. We'll start with circles. Those are fun to do. So before, your equation for a circle was, remember, x squared plus y squared is equal to r squared. But now we can just think about radius and our angle measure theta. So to figure out, just to do a regular circle that's centered at the origin, all you have to do is say what your radius is going to be. So if I had an r equals 4, that's going to say I have a circle that has radius 4. There's nothing else involved, so it's going to be centered at the origin. So if you type that in, r equals 4, this is a circle with radius 4. Okay. If you're just using r equals a number, you can't have it to where it's centered anywhere else besides what your origin in, besides the origin. Okay. And if we think about what the r stands for and the actual equation of a circle and rather an xy form, remember I said circles are x squared plus y squared equals r squared. And every time that we tried to figure out what the radius was with your vectors, or when you're trying to find it out when we were doing the unit circle stuff, when we found our r, remember we said r was the square root of x squared plus y squared. So every time that we found that. So if you'll see, these two coincide, what our radius would be, which is the square root of x squared plus y squared. So it all kind of comes full circle for that. We just ditch our x squareds and our y squareds and just replace it with the number when you're in polar coordinates. And I'm not going to make y'all switch back and forth for equation mode. That's a whole section, but that would take a lot longer than what we have to do. So we're just going to look at what the graphs are, and you're going to graph those. So that's your circle that's centered at the origin. Now we'll do some that are not. So these are kind of neat to see. So our first kind is the ones that are reflective about the y-axis. So we've got r equals a sine theta, where a is just any number that we plug in. So let's look at that. I'm going to type it into here, and I'll show you how to type in a theta. So let's add a 2, no, let's do 3. 3 sine. If you want theta to go in there, just type in the word theta, and it shows up. Okay, so we have r equals 3 sine theta. So if you look at this, our circle is reflexive about the y-axis, which sine always goes with y. Okay, and then its height, it's going from 0 to 3. So that's 3 things. 1, 2, 3. So if you want a circle that reflects on the y-axis, and you want to know like a certain distance or how far it's going to be, that's all we have to do is we just do a sine theta. That gives us our circles that are reflective about the y-axis. This one goes to 3 because there's a 3 in the front that I typed in there. Okay, so this is going to be y-axis circles, and I think you can guess if I change that sine to a cosine, what's going to happen. If I change it to a cosine, and then it's going to be on the x-axis. Okay, so you can draw circles that way for this. So if you're wondering, like, how does this equation provide this circle, you can make a table of values just like you do for x and y graphs, but instead of plugging in an x value or a y value, you plug in a theta value. So if I wanted to figure out what this looked like without having a computer, I would just pick some angle measures. So I would start with at 0 degrees. If I plug that in, cosine of 0 is 1, and then 1 times 3 is 3. So if I'm at 0 degrees, I would plot the point 3. Then maybe I would go over to pi over, I guess I could do pi over 6. Pi over 6, I'll plug that in. Cosine of pi over 6 is, what's cosine of pi over 6? Root 3 over 2. So do root 3 over 2 times 3 and figure out the decimal value, and it would probably be, it looks like it's 2 point something. Okay. You could go to pi over 4. Check that out. Cosine of pi over 4, root 2 over 2 times 3. that would give you whatever this value is right there. Okay, you would plot these points that you're getting, plot, 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 and then connect them, and that would give you your circle. Pi over 3 is a half. 3 times a half is 1.5, so at pi over 3, I am at 1.5. And you plot those points and you connect them together. But I'm not going to have you make all your tables. All you have to do for me is just be able to differentiate x-axis and y-axis and know what the number in the front means. So those are our circles. The next kind we're going to do are roses. They don't really look like a rose. They look more like a daisy to me, but they're called roses. And these are the equations that we'll use and what the numbers mean, and then I'll just show you a couple pictures. So these are our two equations for roses. R equals a sine n theta. There's a number in front of the theta for these. There's not in the circles. There is in the roses. So R equals, then the other one, cosine n theta. And just like before, if it's a sine graph, it reflects on the y-axis. Cosine graph on the x-axis. Okay. And the A stands for how long the petals are, and the N is going to tell us how many petals we have. So the A is the petal length, and the N is the number of petals, but it differentiates if the N is even or odd. So if the N is odd, there are N petals. If the N is even, there are 2 N petals. And I'll show you what that means more when I graph one real quick. So let's see. I graph this one. Let's see what I get. I'll do a sine one first. So I'm going to go, I'll do 4. 4 sine 3 theta. So 4 sine 3 theta. So our petal length is 4. So if I go 1, 2, 3, 4, yep, they're hitting at 4. The N is an odd number, which means that's exactly how many petals I have. I'm going to have 3 petals. And since it's a sine, you can fold it on the y-axis and it's going to match. All right. Now let's see what I would do if it was a cosine. 4 r equals 4 cosine 3 theta. Oh, that's funny. So the cosine, I'll turn the sign off. So cosine looks very similar, except that it's reflexive about the x-axis rather than the y-axis. Okay. All right. So that's with an odd number of petals. I'll do an even number and see what happens. So let's say 2. If I put 2 in there, you might think, oh, this is going to be 2 petals, but it's not. It's 4. So if there's an even number in there, they're double that number of petals. So 2. All right. And those, that's fun. So the sine ones reflects around about the x, or about the y, and the cosine about the x, which for an even number, it actually does both, but that's fun to look at for the overlap. It's kind of cool. So just to make sure we're good, if I put 4 in there, how many petals are there going to be? 8. If I put 6 in there, there'll be 12. If I put 10 in there, there'll be 20 petals. Okay. All right, so those are our roses. Petal length is the number in the front. The number of petals is determined by the N. The next kind of graphs, these are called limaçons. It's a French word. It's got one of those weird curly things underneath the N. I mean underneath the C. So L-I-M-A-C with a little tail thingy. Weird thing. O-N-S. So these are limaçons. And limaçons are shapes. You can get some heart-looking things. You can get what are called cardioids, some lima bean-looking things and stuff with loops in it. They're pretty neat. So here are the equations for our limaçons. We've got R equals A plus B sine theta, and R equals A minus B, not minus, to plus cosine. There can be a minus or a plus in there. If you have a minus, it's still going to be a limacon. It just has to do with the difference in the x and the y values there. Okay, so we have 4 different things that can show up based on what the A value is and what the B value is and how they relate to each other. The first kind of limacon that we can graph is a loop. And a loop happens when your A value is less than your B value. So if I typed in, let's see, I'll do a sign one where A is less than B. So I'll go 3 plus 4, what did I do? I don't want a subscript. Plus 4 sine theta. So this is a limacon. A is less than B. It's a loop, and you'll probably see why it's a loop because it's got a loop in it. It loops all the way around. And what these values are, they correspond to the 3 and the 4. So if you look on the x-axis, we cross at the x-axis at 3 and -3. That comes from the A value. Okay. The number at the top, that's 7. We get 7 from 3 plus 4. And the number at the bottom where we hit right there is 1, and you get 1 from 4 minus 3. So if you do A plus B, you get the top number. A or B minus A, we get the number here for our loop. And it will cross always at the A value. So that happens with those graphs. But you can tell it's a loop if A is bigger than B. All right, now let's see what happens if A equals B. Cardioid, that's what that's called. So if A equals B, so I'll change this to a 3. And we'll do a cosine just so you can see. Ooh, that's funny. Looks like a cosine. So we've got 3 plus 3 cosine theta. They equal each other. We don't have a loop anymore. It looks like a kind of like a heart. That's why I call it a cardioid. But if you see the same thing, we cross at 3 and 3. That's from our A value. 3 plus 3 is 6. 3 minus 3 is 0. So that's what we get from that part. Those are cardioids when the A and the B equal each other. The next kind is called a dimpled limacon. And this is when A is greater than B. There's kind of a like a ranking here, or kind of a threshold. We have A is greater than B, and our last one is going to be A is greater than 2B. So some people don't even talk about the last one, which is the convex one. But they do have different names for that. So we'll do an A is greater than B and then 2B and see what the difference is. So if A is more than B, let's just do 4 and 3. 4 and 3, okay, that works. It kind of cuts it off over there. I'll move it over. Scoot. So that's just got a little bit of a dimple in there. It doesn't have a loop. It doesn't have a sharp point. That's our dimpled limacon. And then if A is bigger than 2 times B, so let's say that was 7 instead. Oh, my gnome locks on. There we go. If it's bigger than 2 times B, you just have like a convex one. You don't have that good dimple. You don't have a loop. And that's what that looks like. Okay. So those are our limacons. We have our loops, our hearts, our little bit of a dimple, and then ones that are like a kind of almost a circle, but you just kind of cut in a little bit right there. But you get the numbers the same way. 7 come from A. 7 plus 3 is 10. 7 or 3 minus 7 is -4. So that would be there. So A plus B here, B minus A here, A and A. And obviously it's rotated if it's a sine graph rather than a cosine. Those are limacons. Next kind are called lemniscates. These are really fun names to say. Lemniscates are going to give us the shape that's like an infinity shape. So r squared equals a squared times sine of 2 theta. And for these, we only use sine. I mean, I guess you could use a cosine. I've never used a cosine before for this. Okay. So I would just put something that's a perfect square in here. I'd do 16 because that'd be 4 squared, and we'll see what happens for that. But I can't type r squared into Desmos. I have to actually rewrite it as a square root. So if I'm going to type this into the computer, I need to do it this way. So I'll come type that in. So we'll do square root. To do square root, you do SQRT. SQRT makes the square root. I'll just pick 16 because that's a perfect square. 16 sine 2 theta. Okay. So 16, that was 4 squared, so it goes out 4 units. And it's sideways. Actually, we do cosine because cosine goes this way. So sorry if I didn't say that before. So for the sine graphs, they go like a crazy infinity to the side. But a cosine graph, if I typed cosine in instead, that's going to be a flat infinity. Pretty sure. Let's make sure. Yep. And cosine is just going to be a flat one. So if you see it that way, that's going to be the cosine one. So you might want to write that down too. R squared is a squared cosine of 2 theta, and that's going to look like this, where the number that it goes out to on either side is just going to be the value of a. So if that was a 9, this would be 3, because that's the square root of that. Okay, so those are our lemniscates. That's the infinity shape. If you wanted to draw on your picture like what that looks like, that could be a loop one, and then a heart-shaped one with a little dimple, one without much. Okay. And our last kind, these are called the spiral of Archimedes. The spiral of Archimedes is where your r is going to equal some number times theta. So as you are going around the circle, when you're plugging in different numbers for theta, since you're going around and getting bigger, your r is going to get bigger as you're doing that. So you're increasing your radius all the way around. Oh, these are really fun to look at. I'll just do r equals theta. That's the basic one. R equals theta, and this one went from 0 to 12 pi. So as I'm going around the circle, my radius is the same length as what my angle measure would be, like in decimal form. So it's getting bigger and bigger. You think once you go around one time, or half the way around the circle, that's pi, which is 3.14, all the way around the 6.28 for 2 pi, etc., and it goes around in a spiral. But I could do like r equals 2 theta, and it's going to be bigger. If I want a tighter one, I want something smaller, 0.5 theta. It's going to be a little bit smaller there, so for that. So that's your spiral of Archimedes. Okay, and those are all of our graphs and how to plot the points. Your homework problems are multiple choice graphs today that you have that'll have like an equation, and you've just got to figure out, it'll be a sine or a cosine. You just think, is it x-axis or y-axis, and how far should it go out? And if you're stuck, you could always go into Desmos and type it in and look at it. I don't care if you do that for your homework assignment today, but just let me know if you have any questions. We have our circles, our roses, limasones, lemniscates, and spiral of Archimedes. And thank you very much, and have a good weekend.